Let's examine free body diagrams. Here's our objectives. When we want to look at all the forces acting upon an object, it's best to use a free body diagram. That's an image which shows the magnitude and direction for all the forces acting on an object of interest. And similar to motion diagrams, we won't be drawing any objects. We'll just draw squares and arrows. In our first example, our object of interest will be a cup of tea. To measure the forces acting on it, we can use a tool called a spring scale. We can measure the force needed to pull the cup, and we'll measure the force of gravity acting on it. So how do we draw a free body diagram for a cup of tea being pulled across a table? First we draw a box, then we use arrows to show the forces acting on it. Using the spring scale, we see that we applied a force of 3 newtons to pull the cup, and the force of gravity pulling down on the cup is equal to -7 newtons. By looking at these arrows, it seems the cup should be moving down and to the right. Since it's not, I think we're missing something. Let's define some common forces. We've already introduced 2. Weight is the force of gravity, and an applied force is a push or pull caused by a living thing. Friction pushes against any object in motion, and air resistance is a form of friction caused by air. Normal force is a supporting force between solid objects, and buoyancy is a supporting force involving fluids. Tension is supplied by a rope or a cable, while thrust is caused by an engine or machine. These are all the forces we'll be discussing. Since the cup is not moving down, there must be some force holding it up, supporting it. That's the normal force provided by the table. And there's also some friction. Now that we have the complete picture, what do you notice about all of these forces? They are equal and opposite to each other. This means all the forces are balanced. Balanced forces are when the net force equals 0. The object is either not moving or moving at a constant speed, just like our cup of tea. Before we move ahead, I must stress the difference between 2 equations. Most people have heard force equals mass times acceleration, but that's an incomplete definition. These are the 2 equations we'll use: acceleration due to a net force and acceleration due to gravity due to the force of gravity. The difference is this: a net force is caused by unbalanced forces, and this makes objects accelerate, which is to speed up, slow down, or change direction, while Fg represents the force of gravity, pulling downward, which is also known as weight. While nearly everyone uses the letter G to represent acceleration due to gravity, I believe it creates a lot of confusion, so I always label the acceleration due to gravity as A sub g. And on Earth, the acceleration due to gravity is a constant value we've used before of -9.8 meters per second squared. Now we can look at 4 more examples of the teacup on the table. First, the cup is at rest. Then the cup is pulled with 5 newtons of force. Then the cup slides across the table on its own. And lastly, the cup falls off the table's edge. How do we show the 7 Newton cup is at rest on the table? This one is easy. The cup has a weight of negative 7 newtons, which is supported by the 7 Newton normal force provided by the table. Since the forces are balanced, the net force is 0, the acceleration is 0, and it isn't moving. How about the 7 Newton cup pulled with a force of 5 newtons while experiencing negative 3 newtons of friction? Since the most friction this table can create on the cup is negative 3 newtons, the forces will not be balanced. The net force is plus 2 newtons, and it will accelerate across the table. How many forces are acting on a sliding cup? It's important to remember that an object in motion stays in motion, so does the cup need a force to keep it sliding across the table? No, there's only friction, no pulling force, so the net force is negative 3 newtons, and this negative acceleration slows it down. And finally, the cup falls off the table. How many forces this time? Yep, just one. As it falls, the only force acting on it is gravity. The net force is negative 7 newtons, and the acceleration is negative 9.8 meters per second squared downward.